unless the strong exponential time hypothesis fails. So this was proved for the eddy distance by Backus and Intig. Then Brinkman and Kuhneman generalized this result for any set of weights that does not admit a trivial solution. Say that the cost of a mismatch is 0 and everything else is very expensive. And then a result of Abud et al. Showed that actually we cannot even hope to slash arbitrarily large polylogarithmic factors from the n-squared time complexity. Okay, and notice that the dynamic programming algorithm filling this DP matrix is inherently online in the sense that characters can arrive one by one, and then we just have to create a new row or column. And also, if we want to delete the last character of either of the strings, we can also process this in linear time by deleting the last row or column. And there has been a significant body of work on the problem of also prepending characters to either of the strings or deleting the first character. I think the most general variant was studied by Tiskin in his monograph on LCS and related problems, on which we will say more about later in the talk. And there he was able to append, prepend, delete in the beginning or the end of either of the strings and proceed such update in nearly linear time. But we instead considered a more dynamic setting where we can update letters anywhere in the two strings. And to update, I mean, we allow insertions of letters, deletions of letters, and substitutions of letters. And the static lower bound that says that we cannot hope for strongly subquadratic time algorithms for the static versions means that for this problem, we cannot really hope for strongly sublinear, because then we could use this, a dynamic algorithm with faster update time, to the static version. Okay, so what we do is when weights are constants, we essentially match this lower bound. So we saw a nearly linear time update time algorithm. And when weights are integers bounded by some W, it's O tilde n times W. Tilde here encoded hides polylogarithmic factors in terms of n and W. And this is based on Tiskin's algorithm for efficient distance multiplication of simple unit ones matrices. We will define everything in a bit. And when weights are large, maybe this is not very satisfactory. So we saw an algorithm that has update time into the 3/2 when weights are polynomially bounded in the length of the strings. And for this, we use some tools from planar graphs for efficient shortest path computation on planar graphs. And this could be interesting to people in the community because it might be applicable to other related problems. That's why I want to present it. So let's see. So focusing on the LCS problem, we define the weight of matching a pair of characters to be 1, the weight of mismatching to be 2, and a gap in either of the directions to be 1. And then the LCS of the strings, the length of the LCS of the strings is equal to the total length of the two strings minus the distance from this topmost leftmost node to the bottommost rightmost node. Essentially, a pair of matching characters is sorted. Okay. So we define a distance matrix from all the red nodes to all the blue nodes, sorted in this order. This is important for the next thing we will say, but let's not go too much into that. And let's see what is a Monge matrix. So a matrix M is Monge if for any I smaller than I prime and J smaller than J prime, M of I comma J plus M of I prime comma J prime is at most M I prime comma J plus M I J prime. So maybe the colors will help you see what this is. So the sum of these green guys is at most the sum of these guys. And in fact, the distance matrix that we define has this property, is Monge. And in fact, this unit Monge, which we will define in the next slide. So given a matrix M, let us define the following operation to construct a matrix M prime. So the matrix M has an entry in each of these cells, and the matrix M prime will have an entry in each of the blue dots. And now we get a matrix of M prime by this operation. So this red dot is equal to B plus C minus A minus D, where these are the neighboring entries on this picture. Okay? And if M is Monge, this M prime is non-negative. In particular, if this M prime is a permutation matrix, then M is unit Monge. And I don't want to define unit Monge in another way because it's a bit technical. And what is important about this is that an n times n unit Monge matrix, although it's of size n squared, can be represented in nearly linear space by exploiting this permutation representation, and by using some data structure on range queries, we can retrieve every actual element of matrix M from such a representation in nearly constant time. So it is important to know that we can represent this space, these matrices in such small space, and this gives us hope that we can also maybe do things with them in time nearly linear in terms of n, and not of the size of the matrix. Okay, and a few more definitions. So the distance product of two matrices, and then times k matrix and the k times n matrix, or mean plus product, maybe, whatever you prefer, is the matrix defined by this expression. So Cij is equal to the minimum of ai comma r plus br comma j. So let's see maybe what this means in an example. So consider this grid and consider the distance matrix from the red dots to the blue dots, and from the blue dots to the green dots. Now observe that any path from the red dots to a green dot must cross a blue dot. So if we multiply A times B, we capture such paths because we will get the minimum of, so suppose we want the distance from the ith blue dot to the jth green dot. So we'll get the minimum of ai comma r, where r runs through the blue dots, plus the distance from r, the rth blue dot, to the jth green dot. Okay, so the distance multiplication of A and B gives us matrix C, which is the distance matrix from the red dots to the green dots. And one of the main contributions of distance work on this area is in showing that the distance product of two n times n simply unit Monge matrices can be computed in nearly linear time, that is n log n, while the matrices are of size n squared. And essentially, the first part of this talk, where we saw the n times w algorithm, is just applying these results to the problem that we consider. And yes, up to here, nothing is new. So now comes the application of this strong tool. So what we want, we have the alignment graph from before. And what we want to maintain is a distance matrix, as shown before. But we want to be able to update this. And notice that if we have the distance matrix, in particular, we have the distance from the topmost leftmost node to the bottommost rightmost node. And this is all we need to find the length of an LCS. So what we do is we maintain the compositions, a logarithmic number of them, a hierarchy of the grid into 2 to the I times 2 to the I blocks. And for each block, we maintain a distance matrix. And then suppose that this letter A changes to a B. Which distance matrices does this affect? So in the bottommost level, level 0, it will affect n many distance matrices of size, of constant size. On the second level, it will affect n by 2 matrices, and in general, on the ith level, it will affect n by 2 to the I matrices. and they will be of size 2 to the I times 2 to the I. So we continue doing this process, and we update all matrices while doing this. And how do we update the matrices? So we rely on this efficient distance metric multiplication. So from the 4 distance matrices of these 4 chunks, which we have computed in the previous level, we distance multiply them, and we can get the distance matrix in the level above. And the computation requires time. So recall that at the ith level, our matrices have size roughly 2 to the I times 2 to the I. So the distance multiplication takes this much time. By the theorem we stated this before. And overall levels, this sums up to n log square n time. And yes, I'm going a bit too fast. Maybe. So we just showed substitutions. And in order to handle insertions and deletions, all we need to do is to carefully resize blocks and maintain this hierarchical decomposition. So when a block becomes too big, we just split it into 2. And when blocks become too small, we merge them with their neighbors and maybe split again. But this is fairly standard. And this was about computing the distance, so the length of an LCS. But the actual LCS can be retrieved within the same time complexity by tracing back the computation. And in fact, our data structure allows us to do a bit more. So suppose you want to query for the LCS of an arbitrary substring fragment of S and an arbitrary substring or fragment of T, then we can do this in n log square n time by composing the appropriate distance matrices. Okay, and now I promised general integer weights. And for this, again, we use some reductions on by T-skin, that if you want to align two strings with integer weights at most W, then you can reduce this to the LCS problem for strings of size by blowing up its letter to a string of size W. So this adds a W multiplicative overhead in our time complexity, and the update time becomes n times W. And what I will present next is, as I promised, an algorithm for the case that W is too large and we cannot afford to pay it. And instead, we'll spend n root n time. Okay. So again, I need to define some primitives from planar graphs. So given a graph of, sorry for the noise, given a graph of a planar graph, we can construct in nearly linear time, in the size of the graph, a data structure that can then be queried and answer such queries in logarithmic time for the distance between any node on the infinite face of the graph to any other node in the graph. So this is somehow a restricted distance sorting. So in particular, in this figure, we can query for the distance from any red node to any other node of the grid. Okay. For instance, if you consider just the vanilla alignment graph, then LCS can be computed just by computing this data structure and querying it for the LCS. We'll just pay a log more. Okay. And then the distance matrix in particular, suppose that we want to compute the distance matrix in this graph. We can compute the MSSP data structure and query it for all pairs of distances. And how much will this cost? Computing the MSSP for a graph of size 8 takes nearly linear time in terms of 8. And if we have these many vertices on the infinite face, then querying for all pairwise distances takes this much time times a logarithmic factor that its query costs. And in the planar graph community, these distance matrices are usually called dense distance graphs and are represented as complete graphs on these many vertices. And what is important is that FR Dijkstra, a result by Factsaroinfol and Rao, says that we can compute shortest paths, single source shortest paths, on a union of dense distance graphs in nearly linear time with respect to the number of vertices of those distance matrices. So one can give us distance matrices. It's many of them, of maybe some, okay, on a total number of capital N vertices. This means that we may have quadratic number of entries in these matrices, but then we need to spend only this much time to do shortest path computations. So for instance, consider again one grid and consider that we have the DDG for each red square. Okay, the dense distance graph for each red square. Then we can, from any vertex that is red, we can compute shortest paths to the whole graph using these DDG edges. Okay, so before we discussed about distance product of a pair of distance matrices. Now we may have many distance matrices which share some vertices, and we can do shortest path computations efficiently. And this algorithm by Factsaroinfol and Rao is again, they were able to design it because they exploited Emon's property again, which is the same reason that our distance matrix is defined above half the Emon's property. So consider a planar graph and consider vertices u, v, x, and y on the infinite phase. And I will try to prove this. It is known, I just think it's nice. So we want to show that the distance from u to x plus the distance from v to y is at least the sum of the distances from u to y and from v to x. So let us consider, so this is a planar graph, right? So these paths must cross somewhere, the two paths that I have drawn. And because it's a planar graph, they must cross at a vertex. So let us focus on the distance from u to y. This is at more, they have the option to go through z, right? We know there exists a u to z path and the z to y path. So we could use this, or maybe there is something cheaper. But certainly the distance from u to y is at most the distance from u to z plus the distance from z to y. And similarly for the distance from v to x. And I hope that I did convince you that we have the Emon's property. And now let us see how to apply FR Dijkstra and MSSP to our problem. So again, consider a grid. We will split into a linear n pieces, each of size root n by root n. And for each of them, we will maintain the distance matrix, or DDG. So this piece has size n, theta of n, and the red nodes, so the boundary, is of size root n. So how many pieces does an update in one of the strings change? It changes root n of them. And for each of them, using MSSP, we call each of them has linear size, and we need to do root n times root n queries for computing all of the red to red distances. So each of them can be updated from scratch in nearly linear, in n root n time. So each of them in n time, and all of them n root n time. So have root n of them to get updated, and each of them takes linear time. Okay, and finally, we just need to run FR Dijkstra on the union of all those DDGs. And we have n DDGs, each of them is of size root n. So this runs in n root n as well. And we get some balance. Okay, this concludes this result. So now some final remarks. So we can also handle copy-paste operations with these techniques. That means take a fragment of one string and move it somewhere else, but in the same string, copy-paste it. and some open problems maybe. So one obvious one is, can we improve this n to the 3 halves for large weights? And another thing is we could maybe consider one of the strings to be a straight line program. And for the static case, as also discussed in the previous talk, we can achieve if one string is standard and is of length small n, and the other is given by an SLP of size capital N, then their LCS can be computed in small n times big N time, hiding all logarithmic factors, a single logarithmic factor. And the third thing is there has been this large body of work on approximating the eddy distance or LCS in the last few years. And the most recent paper I'm aware of is by Andoni Nozatsky, saying that we can constant factor approximate it in n to the 1 plus epsilon time for any constant positive epsilon. And perhaps other problems that have been considered and are of the same flavor is the dynamic longest increase in subsequence. The distance to monotonicity, this is a recent paper. And this is all. Thank you very much.
Thank you, Pano. Nice talk. I have also asked on the chat, does anyone have